It's generally thought that all polynomial equations have a solution. However, we hit a bump when we consider problems such as I squared plus 1 equals 0. When we solve this problem for I, we find I squared equals minus 1 and I equals the square root of minus 1. As we know, this solution cannot exist. Basic maths principles tell us that there is no real number with the negative square. So how can we solve this problem? We can allocate the symbol I to represent the square root of minus 1. We call I an imaginary number. It allows us to solve problems algebraically. For example, to find the product of 6i and 7i, we multiply 6 and 7 to get 42i squared, which equals minus 42. A complex number itself comes in a pair of two real numbers in the form z equals x plus iy, where z is the complex number, x is the real part of the complex number, and y is the imaginary part of the complex number. On the Cartesian plane, we represent the real part on the horizontal axis and the imaginary part on the vertical axis. The addition and subtraction of complex numbers is essential to work many of the equations necessary in electrical engineering. If we wish to add two complex numbers, z1 equals a plus ib and z2 equals x plus iy, we use the following formula: z1 plus z2 equals a plus x inside brackets plus I multiplied with b plus y inside brackets. For an example, we're going to add two complex numbers, z1 equals 2 plus 4i and z2 equals 3 plus i. So z1 plus z2 equal 2 plus 3 inside brackets, plus I multiplied with 4 plus 1, which equals 5 plus 5i. The AC power source produces two in-phase sine waves of voltage and current. Adding a resistor doesn't change the phase angle of these sine waves, but adding either a capacitor or inductor manipulates these sine waves, shifting them horizontally along the negative or positive x-axis. It is these components that introduce the need for complex numbers. By using complex numbers, we are able to obtain the total current impedance, voltage drops, and total current of the circuit. The angles associated with resistance, capacitance, and inductive reactance on the complex plane diagram are shown below. Resistors have an angle of 0 degrees, inductors have an angle of positive 90 degrees, and capacitive loads have an angle of negative 90 degrees. To find the total impedance of the circuit, we do complex number addition of the three components, resulting in the impedance Zt equals 7 plus minus 2i. To find the phase angle of the total impedance of the circuit, you simply find inverse tan of the real and imaginary coordinates. If a circuit's phase angle is positive theta, then the circuit is an inductive circuit. If theta is negative, then the circuit is capacitive. Being able to calculate this angle is useful in real life. If a circuit is found to be too inductive, energy consumption and bills will increase. By adding capacitors, we can reduce the angle of theta and therefore reduce unnecessary power consumption. Finding the total impedance value of the circuit is just a matter of using the Pythagoras theorem in the real and imaginary coordinates.